Let's continue where we left off yesterday. Remember the main idea behind any model. It's not necessarily financial, or although I'll always take my examples from that specific field, is F. F being the exact relationship between your inputs and outputs. When we talk about estimating F, we have limitations creep in. You're not necessarily looking at the full extent of the variables influencing the output. Even if you did have that data, the relationship, so think of just a mathematical expression, a formula, the relationship that one derives isn't necessarily going to be perfect. And this is why, in fact, we don't really use F, but we'll use F hat. Let's start reading. Throughout this book, we explore many linear, this is yesterday's last page. Throughout this book, we explore many linear and nonlinear approaches for estimating F, keyword estimating. However, these methods generally share certain characteristics. We provide an overview of these shared characteristics. So I guess this section is where we're going to establish the notation and certain features that will probably be a common theme throughout the book. We will always assume that we have observed a set of n different data points. And again, what is your data point? We mentioned patients yesterday undergoing a specific medical trial. The first example in this book was wage data. So your data subject was employees, their annual salary. Going back to the usual insurance examples, it could be a policyholder, it could be an insurance company, it could be a specific portfolio. And we will usually the more data points, the better. To a certain extent, you have less variability, and you also have I guess a stronger likelihood that your data is reflecting all the possible outcomes. In a small data set, what might look like an outlier, if you had to increase the number of data points, it might very quickly emerge that it's not in fact an outlier at all. These observations are called the training data, self-explanatory, because we will use these observations to teach the method that we're using. So think linear regression, for example, how to estimate F. Now, it's a two-dimensional array over here. Think of just a rectangular block of data in Excel, where each I represents a row, and within each I, we have J. J is, this is a quick repetition, by the way. I'm seeing the chat. This page, I think it's worth repeating it very quickly, just to make sure that we're definitely 100% sure of the notation. But you are correct. This is repetition. Xij represents the value of the jth predictor or input for observation I, where I runs from 1 to n. It's the same n data subjects. J is from 1 to p. The output, that's a single index. It's yi. Yi is the response variable for the ith observation. So aggregating these xij's and yi's gives us, think of it as a database, x1, y1, but x1 is this vector. And the book is reminding us time and time again our goal is to apply statistical learning to the training data in order to estimate the unknown function f. In other words, we want to find a function, and we're going to read this as f hat, such that the true y value, the true output, is approximately f hat x. Now remember, f hat x will give you y hat, and you're hoping that this y hat, your estimates are approximately equal. Now, whatever we mean by approximately equal to the true output value, and this holds true for any observation x. That's your training data, together with the output. The output is within the training data as well. The distinction is we're using x to predict y. Broadly speaking, most statistical learning methods for this task can be characterized as either parametric or non-parametric. We're going to go into the non-parametric today. We now briefly discuss these two types of approaches. Parametric methods, and I'm going to skim through this section, especially if, I guess we can always go back and watch the recording if you'd like to revise this. An example, this is just an example of a parametric method, is assuming linearity between y and the predictor variables that we're using to model y, and this will be chapter 3. Once you've estimated beta naught to beta p using, for example, least square regression, then you now have a model-based approach, which is described as parametric, and you've taken the problem of estimating the output down a notch. You've made it more accessible. Linearity makes it a lot simpler, and we mentioned A-level yesterday. You're passing that plane, so it's a linear surface. And we're speaking of surfaces because we're only allowing for 2 predictor variables, the yours at school and the yours of actual work experience. This plane passes through these points, and it doesn't pass exactly through them because it's not a perfect model. Instead, the distances between each red point and the plane, that gives you a measure of the error. Remember, we had epsilon in our formulae, and I would imagine we're going to see it somewhere over here, that captures the variability or the error. It's also known as an error term. Assuming parametric form for f simplifies the problem of estimating f, because it is generally much easier to estimate a set of parameters, and we're denoting the standard notation, by the way, as beta naught until beta p in the linear model than it is to fit an entirely arbitrary function f. Now, the potential disadvantage of a parametric approach is that the model we choose, so there's a choice over here, right? I'm choosing to model based on the assumption of linearity, will usually not match the true unknown form of f. If the chosen model is too far from the true f, then our estimate will be poor, and there are many ways of measuring how good one's estimate is. We can try to address this problem by choosing flexible models that can fit many different possible functional forms for f. But in general, fitting a more flexible model requires estimating a greater number of parameters. So it's computationally, that's going to be more intense, and you even have the data in the first place. How extensive is the training data? And even if it's an insurance company, you don't want to ask a prospective policyholder too many questions. Number one, if it's an online application, I mean, how many of us over here have started an online survey only to realize 5 minutes in that we're not even 10% through? It happens to me easily once a month. And it's not like I'm filling surveys all the time, but one's appetite for filling a survey usually is not infinite. But in general, fitting a flexible model requires, this is what we just said, these more complex models can lead to a phenomenon known as overfitting the data, which essentially means that they follow the errors or noise too closely. Remind me one of these days, speaking of overfitting, we're familiar with the, what is it? What's the name of that scientist? Our solar system, we have a heliocentric, and that wasn't Kepler, was it? It was Copernicus, right? The Copernican model. Well, yeah, exactly. Thank you. The Copernican model of our solar system, which is widely accepted to this very day and has proved to be very effective in, for example, predicting the position of new planets, which cannot be observed with the naked eye. You really need to know what you're looking for with a powerful or relatively powerful telescope to identify them. Well, that replaced, I'm going to call it the Aristotelian model. It wasn't Aristotle, but I'll use Aristotle as a placeholder. Well, it was still an empirical model. So we know the story of how at one point the scientific consensus was Earth at the center of really the observable universe at that point. We hadn't gone really that further than the outer boundaries of the solar system. Well, that was a case of overfitting, where the model maybe followed too closely, especially the errors. So those errors creeping in to the point that your model actually breaks down very quickly when you actually try predicting unobserved data. These issues are discussed throughout this book, as you can imagine. I think we're going to skip this. This is a more refined model, and we're referring to it as a thin plate spline fit. The spline is generalizing the linearity. And I think now we can actually move on to the non-parametric methods. Let's have a look. Non-parametric methods do not make explicit assumptions about the functional form of f. Instead, they seek an estimate of f that gets as close to the data points as possible without being too rough or wiggly. Such approaches can have a major advantage over parametric approaches by avoiding the assumption of a particular functional form. So, for example, by avoiding that it has to be linear, they have the potential to accurately fit a wider range of possible shapes for f. Any parametric approach brings with it the possibility that the functional form used to estimate f is very different from the true f, in which case the resulting model will not fit the data well. Now, in contrast, or at least so the theory goes, non-parametric approaches completely avoid this danger, since essentially no assumption about the form of f. When we say form, again, is it linear? Is it quadratic? Hey, who knows? Trigonometric, logarithmic, just your standard functions at secondary school and post-secondary. But non-parametric approaches do suffer from a major disadvantage, since they do not reduce the problem of estimating f to a small number of parameters, a very large number of observations, far more than is typically needed for a parametric approach is required in order to obtain an accurate estimate for f. So this would appear to be the price that one pays. If you're going for non-parametric, then as a rule of thumb, you would need what's being described as a very large or a much larger number of observations than when working with a parametric model. An example of a non-parametric approach to fitting the income data is shown in figure 2.5, which is actually, okay, this is actually parametric apparently. Let's have a look. Oh yeah, that is parametric. I guess now we're going, no. So an example of a non-parametric approach is 2.5. So this is non-parametric apparently. Okay. A thin plate spline is used to estimate f. This approach has not imposed any pre-specified model of f. It instead attempts to produce an estimate for f that is as close as possible to the observed data, subject to the fit. Meaning, as you would expect, the error bars in this parametric linear model have been reduced in this alternative model, which is giving us an example of a non-parametric approach. Where the model is allowed non-zero curvature. Okay, and I have done something silly. I pressed the button and actually took me to the end of the book. So let's go over here. An example of a non-parametric approach. We've just seen that. I'm going to move on. And I think we can safely skip this paragraph for the time being. Trade-off. This is really everything that you're considering. There's always, it's always at the back of our minds. And this section is the trade-off between prediction accuracy and model interpretability. Of the many methods that we examine in this book, some are less flexible or more restrictive in the sense that they can produce just a relatively small range of shapes to estimate f. One example would be linear regression, since it only generates linear functions such as lines or planes. Other methods, such as the thin plate splines, shown in figures 2.5 and 2.6, are considerably more flexible because they can generate a much wider range of possible shapes. One might reasonably ask the following question: why would we ever choose to use a more restrictive method instead of a very flexible approach? There are several reasons, apparently. If we are mainly interested in inference, then restrictive models are much more interpretable. For instance, when inference is the goal, the linear model may be a good choice, since it will be quite easy to understand the relationship between y and the predictor variables. So, for example, if I increase x2, is y2 going to increase, decrease, and at which rate? In contrast, very flexible approaches, such as Chapter 7's splines, and the spade in figures 2.5 and 2.6, and the boosting methods, which is apparently a very topical subject, even on Kaggle. If you're not familiar with Kaggle, and my own familiarity is, I would say, extremely limited, it's where there are these data science competitions. And I don't know where I was reading recently, but apparently some really high statistic, like 7 out of every 10 or 8 out of every 10 winners, they use boosting. Don't ask me what boosting is. That's why we're all here. And I'm optimistic that we will get to the relevant chapter. And we're saying that if it's overly flexible, it will lead to such complicated estimates of f that it's actually difficult to understand how an individual predictor is associated with the response. So it's more of a black box where, okay, it might be working, but exactly what the sensitivities are of the output y to the inputs x might be harder to really get to grips with. Now, figure 2.7, which is this over here, we're looking at, I would imagine some of them are examples of parametric and others are of non-parametric. And it's probably enough to just read this. A representation of the trade-off between flexibility and interpretability using different statistical learning methods. I guess this would, somewhere in this region, this would be the Goldilocks zone, not too hot, not too cold. So for example, these squares, which would be, your linear regression, not necessarily linear. I shouldn't have necessarily put it that way, but an example is linear regression. Where it's scoring high or close to high on interpretability. The trade-off is it's not that high when it comes to the flexibility. This is an overview of each chapter. I think we can safely skip for the time being. Of course, you have access to this book, so by all means, I think you can do a lot worse than read what we're skipping in your own independent study. And let's move here. So supervised versus unsupervised learning. Most statistical learning problems fall into one of two categories. That's your supervised or unsupervised. The examples that we have discussed so far in this chapter all fall into the supervised learning domain. For each observation of the predictor measurement, there is an associated, so let's back up for a second. So everything that we've discussed so far, this is supervised, where you have inputs and an output. And I think the book is repeating something that we went over yesterday as well. So we wish to fit a model that relates the response to the predictors, with the aim of accurately predicting the response for future observations, or better understanding the relationship between the response and the predictors. Many classical statistical learning methods, such as linear regression and logistic regression, as well as more modern approaches, such as generalized additive models, boosting, and support vector machines, operate in supervised learning approach. So these are all inputs with an output. The vast majority of this book is in fact devoted to this setting. Just very quickly, what is unsupervised learning? The 5-word sentences, there is no response output. It is not possible to fit a linear regression model since there is no response variable to predict. In this setting, we are in some sense working blind. The situation is referred to as unsupervised because we lack a response variable that can supervise our analysis. And this might be an example. So figure 2.8 provides a simple illustration of the clustering problem. We have plotted 150 observations with measurements on 2 variables. So these are 150 of them. We're plotting 2 variables against each other, but x2 is no longer the output variable. It's no longer the familiar scenario where your horizontal axis is your input and the vertical is your output. Each observation corresponds to one of 3 distinct groups. For illustrative purposes, we have plotted the members of each group using different colors and symbols. However, in practice, the group memberships are unknown, and the goal is to determine the group to which each observation belongs. In the left-hand panel of 2.8, this is a relatively easy task. So this is relatively easy. There are clear, or what would appear to be clear demarcation lines. Now this would be more challenging, right? There is even overlap between, from what I can see, the blue and the green, and maybe perhaps as well minor overlap over there as well. Yeah, and in fact, in contrast, the right-hand panel illustrates a more challenging problem in which there's some overlap between the groups. So this is unsupervised learning. And I'm going to make a judgment call. I don't really like doing this. As much as possible, we would read every sentence in the book. But the book itself said we're mainly going to concern ourselves with supervised learning. Regression versus classification problems. Variables can be characterized as either quantitative or qualitative, also known as, so the qualitative is also known as categorical. Quantitative variables take on numerical values. Examples include person's age, height, income, the value of a house, the price of a stock. On the other hand, qualitative variables take one of a finite number of, call them classes, call them categories. Examples of qualitative variables include the person's gender. So that's, well, at least the example we're taking over here, that's binary. The brand of product purchased, 3 variables. Whether a person defaults on a debt, binary again. Cancer diagnosis. No, I'm not going to try pronouncing those different types of cancers. We tend to refer to problems with quantitative response as regression problems, while those involving a qualitative response are often referred to as classification problems. However, the distinction is not always that crisp. Least squares linear regression is used with a quantitative response, whereas logistic regression, but it's still regression, right, is typically used with a qualitative 2-class or binary response. As such, it is often used as a classification method. So you're going to use logistic, for example, whether, so this is something the banks would use to take another example from finance. Is the person a good risk? Is the borrower considered a good risk or a bad risk? To what extent is an individual a bad risk? Would it mean that the bank is going to outright refuse to lend them money, or would it be a case of at a higher rate of interest, perhaps? After all, that's what interest rates do, right? Beyond maybe certain moral objections, which I guess we can only be sympathetic to some of the arguments made there. Interest rates are really just a means of distinguishing between good credit and bad credit. Moving on, but since it estimates class probabilities, it can be thought of as a regression method as well. Some statistical methods, such as k-nearest neighbors, chapter 2, chapter 4, and boosting, chapter 8, can be used in the case of either quantitative or qualitative responses. And that would be classification, I would imagine. We tend to select statistical learning methods on the basis of whether the response is quantitative or qualitative. So we may use linear regression when quantitative, and logistic regression when qualitative. So the nature of the data, the variable that we're trying to predict, that's already going to influence the type of model that we would even consider using. However, whether the predictors are qualitative, now we're looking at the predictors, the inputs, are qualitative or quantitative, is generally considered less important. Most of the statistical learning methods discussed in this book can be applied regardless of the predictor variable type, provided that any qualitative predictors are properly coded. Now, what do we mean by coded? That really you have your buckets and you have a very systematic way of, so if I don't know, if it's hair color, you're going to say, okay, you could maybe just go 3 different colors, right? You could just say maybe dark, so you'd put maybe dark brown and black, somewhere middle of the road, and light. That would be one way of, I usually refer to it as bucketing the data. 2.2. Now we're looking at the model accuracy. So I guess usually this is at the end. This is when you've generated your own prediction values. One of the key aims of this book is to introduce the reader to a wide range of statistical learning methods that extend far beyond the standard linear regression approach. Why is it necessary to introduce so many different statistical learning approaches rather than just a single best method? Of course, that's assuming there is such a thing as a best method. And how would you even classify methods from best to worst? What metric would you use? There's no such thing as a free lunch in statistics. No one method dominates all others over all possible data sets. On a particular data set, one specific method may work best, but some other method may work better on a similar but different data set. Hence, it is an important task to decide for a given set of data which method produces the best results. Selecting the best approach can be one of the most challenging parts of performing statistical learning in practice. In this section, we discuss some of the most important concepts, and we get one of the very few formulae that we've considered until now. As the book progresses, we will explain how the concepts presented here can be applied in practice. Now, just before we start reading this section, notice that we're taking the difference between 2 items that have a lot in common. They are both the output. This is yi, and this is y hat I. And I know it's not really going to make much of a difference writing y hat, but I'm going to write it, well, consistency, I'll use green. So this is y hat I. I think we said green. Y hat I. And you're looking at the difference. Now, I'm sure you've all, just intuitively, you want the difference. Ideally, you want your difference to be 0 for every observation, and we shall keep using n for the number of observations. For each one of them, so for each I variable, did I say variable? For each I input, ideally this would be simply 0. Then again, that might be overfitting, the same overfitting we mentioned earlier. Let's have a look. In order to evaluate the performance of a statistical learning method on a given data set, we need some way to measure how well its predictions actually match the observed data. And we can actually continue using the same colors that we have below. The observed data, its predictions, and using maybe just black, we're going to use this measure. We're going to use this measure. That is, we need to quantify the extent to which the predicted response value, that's green, the predicted response value for a given observation, yes, that's orange, is close, so close, we're subtracting, to the true response value for the actual observation. In the regression setting, the most commonly used measure is what we define as the mean. Mean is a type of average. We're all familiar with median and mode, but it's the mean. In fact, we are dividing by the number of observations, but we're taking the mean of what? Not the mean of the predictions, not the mean of the observed data, but we're taking the mean of the squared error. So when we say squared error, and we're quickly running out of colors over here, I hope the yellow is visible. We're taking the mean squared error, and you want to minimize that, right? In fact, in Kaggle, those competitions I mentioned earlier, and I said that the teams that win, the teams that classify at the top. I wonder if it occurred to anyone, but how are we measuring? How are we classifying which teams should classify? How do we impose a hierarchy on the different models? To my knowledge, or at least in some competitions, mean squared error is the one that's used. Where f hat of xi is the prediction that f hat gives for the ith observation. The mean squared error will be small if the predicted responses are very close to the true responses, and will be large if, for some of the observations, the predicted and true responses differ substantially. The mean squared error is computed using the training data that was used to fit the model, and so should more accurately be referred to as the training mean squared error. Now, and this is a really important point in my opinion, in general, we do not really care how well the method works on the training data. Rather, we are interested in the accuracy of the predictions that we obtain when we apply our method to previously unseen test data. So if we just take a step back from this, and for those of you just joining, we're being introduced in this section to our first formula that attempts to quantify how well our model, think of a linear regression model, think of a non-parametric model, models the data, whatever that means. And the idea is you're going to take the model's predictions and you're going to compare them against the actual observations. So what we're looking at over here is supervised learning, where you have an output and you've been put in charge to come up with a model that relates your input data to your output data. Now, this is known as mean squared error. You are taking the differences between the actual observation and the predicted output. You're squaring and you're calculating the mean. So sigma, we're adding, and then we're dividing by the number of observations. Now, we're not really interested, are we, in the mean squared error on the training data, because it depends on the training data. Instead, we're interested in the accuracy of the predictions that we obtain when we apply our method to previously unseen data. This is the true test of any model. Why is this what we care about? Suppose that we are interested in developing an algorithm to predict a stock's price based on previous stock returns. We can train the method using stock returns from the past 6 months, but we don't really care how well our method predicts last week's stock price. That's already happened. We instead care about how well it will predict tomorrow's price or next month's price. On a similar note, suppose that we have clinical measurements, weight, blood pressure, height, age, family history of disease for a number of patients, as well as information about whether each patient has diabetes. We can use these patients to train a statistical learning method, so that's your historical data, to predict risk of diabetes based on these clinical measurements. But going into practice, we want this method to accurately predict the risk of diabetes for future patients based on their clinical measurements. If you are more susceptible to diabetes, then that means that, at a younger age, you already know that perhaps a certain diet just is going to increase your chances of diabetes. We are not very interested in whether or not the method accurately predicts diabetes risk for patients used to train the model, since we already know which of those patients have diabetes. To state it more mathematically, suppose that we fit our statistical learning method on our training observations. And our training observations are, this is the full data set. Think of a database, think of 10,000 rows of patient records, one line for every data subject, for every patient. And each pair over here represents one line, one record, one observation. And we obtain the estimate f hat. Okay, so now you have your f hat. Now you have your formula. Going back to yesterday's material, think of a formula like this one. Income is approximately equal to beta naught plus beta 1 times education times beta 2 times seniority. Okay, that, if it's a bit abstract right now, you can make it a lot more concrete by just keeping this example in mind. So imagine that this is our f hat. We can go back and calculate and this is the difference, in fact, and calculate. The yellow plane is your prediction. Your red is your actual observation. So we can then compute f hat of the first observation, f hat of the second observation. If these are approximately equal to y1, y2, then the training mean squared error given by 2.5 is small. And do keep in mind, you want to minimize the mean squared error. However, we are really not interested in whether f hat of xi is approximately equal to yi. Instead, we want to know whether f hat of x naught is outside the training data. It's also known as an out of sample observation, is approximately equal to y naught, where x naught comma y naught is a previously unseen test observation. It wasn't used to determine those parameters beta naught, beta 1, beta 2. It is an unseen test observation not used to train the statistical learning method. We want to choose the method that gives the lowest test mean squared error, and test is the unobserved data. Should I put it that way? Yeah, I think that works. As opposed to the lowest training mean squared error. In other words, if we have a large number of tests, not training, of test observations, we could compute the mean squared error. They're choosing to write AVE. Do I understand what AVE means? Let's see, the average squared prediction error for these test observations, x naught, y naught. I think the only reason why they're writing it AVE is because if they're going to use sigma, they have to specify the number of observations. Whereas instead they're just saying we have x naught comma y naught. Would like to select the model for which the average of this quantity, yeah, exactly, the test MSE is as small as possible. How can we go about trying to select a method that minimizes the test MSE? In some settings, we may have a test data set available. That is, we may have access to a set of observations that was not used to train the statistical learning method. In fact, in practice, what one usually does is you get all your raw data and you decide that instead of using every single observation to train your model, one common split is 80%, 20%. You use only 80% of your observations. You randomly select 8 out of every 10 observations to be included in the process of building the model. And then you test that model on the remaining 20%. That 20%, I know it as an out of sample data set. We can then simply evaluate 2.6 on the test observations and select the learning method for which the test MSE is smallest, right? So you could try multiple models, and then for each model, take the predictions and use those predictions to compare against the out of sample data, and you calculate a test mean squared error for each model. And then you could simply pick the model if you're only going to go, if you're only going to consider mean squared error as your way of classifying the effectiveness of the models, you would simply go for the model that has the lowest test mean squared error. But yes,
there was a formula with f hat of x naught and y naught.
yeah.
Yeah,
So,
that one.
so this is just remember from yesterday's notation, yi is the actual observation, and you use those observations from 1 to n to create a model. The model is f hat. The model is f hat. It's usually going to be a mathematical formula. So think of a linear relationship, like a plane. You use f hat to calculate the prediction values. Then you're going to look at the difference between them. And for reasons that we're not going to go into, but basically to get a positive number or a non-negative number, we square. So the difference, that subtraction is giving you these black lines. These black lines, which we described as the error in previous sessions. So what we're doing is we are, let's find 1 point, I don't know, for example, let's take this one. The red, you look at the axis, the income, and the red is the actual observation. The yellow surface, this point, that is the model's prediction. So just take an example. Let's see how well I can.
And when you say observation, what are you, what do you mean?
The raw data. So, for example, you do a survey and you ask everyone in your course at university, you ask them, I don't know, how tall are you? And that's your observation. That's your observation. The model is trying to create a relationship between the observation, so the observation's output value, for example, a person's height, as a relationship with their diet, their parents' height, maybe level of pollution, if they were seriously ill when they were young, and number of calories that they take in every day. So for example, in this case, what do we have? We have, that's interesting. So the way they've drawn this, they haven't actually used parallel lines. You have, for this specific data point, this is the number of years of education. That's the number of years of education. This is the seniority level. I guess just the number of years of work experience. And then you have the income. So imagine that you're just sending out a survey, and you're asking people, how many years did you do at school? That's years of education. How many years have you been in the workforce? That's your seniority. What is your income today? Those three are your observations: years of education, comma, seniority, comma, income. So this specific red point, where were we? This specific, where were we doing this one? This specific red point has, it's at a specific location described by 3 coordinates: number of years in education, the number of years of work experience, and the income. Now, what your model is trying to do is it's trying to create a relationship, just like we know that the area of a trapezium is a plus b on 2 times height. So the area of a trapezium is a function of the lengths of the 2 parallel sides, as well as the perpendicular distance between those 2 sides. We're doing the same thing over here, but we're not modeling the area of a trapezium. We're not modeling the volume inside a cone, but we're trying to create a mathematical formula, an algebraic description that relates 2 inputs this time round, not 3. A trapezium uses 3. If I want to be in a position that I can calculate the area inside any trapezium, then I need 3 specific variables: your A variable, your B, and your H. And those are all lengths measured in centimeters, meters, etc. What we're doing over here is we're measuring in years of education and years of, I think this is years of seniority, to create the income. So red is the actual data. Red is the actual data. The yellow surface is the model's output. So the model nearly never gets it right. So this looks pretty good. So the difference is, you know, a lot less than this difference, for example. Now, how do we judge? How do we judge a model? How do we rate a model? Well, there's this measurement that we're going to refer to as the mean squared error, that's taking those differences between actual and prediction. In fact, even in actuarial science, and it's probably the one thing I'm usually asked about most at work: actual versus expected. You expected that next month the company pays 2 million in claims. Next month comes, it goes by, we now have the data. The company only spent 1 million in claims. So actual versus expected. Your Y is the actual. Your F hat of XI is the expected. Expected according to whom? According to, what are those people called that use tarot cards? Tarot cards, actually. I think the T is silent. According to a fortune teller. Well, that's what we're doing, right? We are fortune tellers. You could use this. You use this today. Look at the weather forecast for tomorrow, and you can perform an actual versus expected once you obtain tomorrow's data. Of course, you're going to have to wait for tomorrow, but tomorrow, when tomorrow does come, and if you do observe the weather tomorrow, you can calculate an actual versus expected. This formula is the same as this formula. The only difference is one of notation, in my opinion. We're using X naught and Y naught. Don't ask me why they've been flipped around. Of course, it makes no difference because we're squaring. Over here, we're doing actual minus expected. This would appear to calculate expected minus actual. But of course, we're squaring everything. So at least in terms of the output, it makes no difference. I would imagine, if I had to guess, there is no specific reason why they are swapped around. Does that help?
Yes, it does. Thank you.
Okay, very good. So the idea is that the X naught is not in the training data. The training data is when you send out a survey. So you go around university and you ask everyone, do you prefer Harry Potter franchise or film universe, or do you prefer the, I don't know, Hunger Games? And you ask everyone. So you're roughly going to get around 10,000 observations. But not only do you ask them if they prefer Harry Potter or the Hunger Games, but you're also going to ask them, what's your age? What is your course at university? How old are you? Where do you live? What citizenship do you have? And then you could try predicting. If you manage to collect that kind of data, you could try predicting, okay, someone who lives in region A is doing course XYZ, was born in this specific year. What is the likelihood that they prefer Harry Potter over the Hunger Games? Now that's once you create the model, then the model gives you the predictions for every combination of inputs. So I can now input whatever I like into the model. I tell the model, what if there's someone born in region B, born in this year, and is doing this course. There may not even be someone who was born in a specific region, doing a specific course, and having a specific age. But you can still ask the model, if there was such a person, if there were to be such a person with these specific characteristics. So remember, to a certain extent, statistics can be a bit dehumanizing, where you're reducing, well, especially if it's statistics working with people, where you're reducing what, number one, you're aggregating individuals. So it's no longer an individual, but you're grouping people into larger categories. And number two, you're reducing them to only a specific set of characteristics. So think of, for example, their sex, their sexual orientation, their religion, their ethnicity, socioeconomic background. So, and, you know, any survey that you've ever filled, if you create an account on social media, so for example, take Facebook, it's going to ask you certain questions. And by the way, it's asking you those questions because it will use that data to feed you the most relevant marketing campaigns. It is pointless if Facebook knows that I'm really into, I don't know, I don't take really any specific examples, but if I'm really into extreme sports, all the photos, all the places I'm tagged in, it's extreme sports. It probably doesn't want to market something that's a totally different, something that I probably wouldn't be interested in. Okay, probably wouldn't be interested in. Well, according to whom? Well, according to the model. But you have various models, and how are you going to test? How are you going to compare these models? And we can continue reading to answer that question. In that case, one may imagine simply selecting a statistical learning method that minimizes the training. This is if you have no test, MSE. This seems like it might be a sensible approach since the training MSE and the test MSE appear to be closely related. Unfortunately, there is a fundamental problem with this strategy. So what strategy is this? Using your training data to calculate your mean squared error. There is no guarantee that the method with the lowest training mean squared error We'll also have the lowest test mean squared error. Roughly speaking, the problem is that many statistical methods specifically estimate coefficients so as to minimize the training set mean squared error. So there are certain models, they're referring to them as many statistical methods, that's the way they operate in any case. It's within their design to minimize the training set mean squared error. For these methods, the training set mean squared error can be quite small, but that's by design. That's by design. So you kind of stacking the deck in your favor. But the test mean squared error is often much larger. Figure 2.9 illustrates this phenomenon on a simple example. Let's read this first. Let's read this first. So, interesting. Class. And we're not a class, sorry, but force of habit. We have what I would imagine is how many models over here. Give me a second. I'm just gonna get my phone. We have how many models over here? And this will be the last thing that we do today. We have, well, let's count them. I'll use red. We have this model, number 1, the green, number 2, the black, number 3, the blue, number 4. So we have these 4 models, and I think they're being represented over here. The model 1, model 4, and maybe model 2. Although the black doesn't appear for some reason. So let's just read this. Data simulated from F shown in black. Ah, no wonder black doesn't appear. So again, just like we discussed yesterday, the authors are playing God. The authors start with a known relationship, that's black. They simulate the data. Now, why isn't the data exactly on the black? Because this is the error term. So they know the true f of x, and they know epsilon. Epsilon incorporates the random error, or the error term. 3 estimates of f are shown. I'm going to refer to them as gold, blue, and green. The linear regression, actually, let's use their colors, orange, and 2 smoothing spline fits, blue and green curves. And this is the mean squared error. But I'm not entirely sure why we have 2 mean squared errors. For the test and the training. Look. So the gray is the training. The gray is the training. And you would think that green is the best. Green has the lowest mean squared error. From the 3, green has the lowest. Whereas in fact, if you calculate the mean squared error on the test data, the data that has not been used to model these observations, and in fact, for whatever reason, blue comes out on top. Blue has the best. Best is lowest in this case. Blue has the lowest mean squared error when using the test data. Remember, the test data was not in fact used to create these 3 models, the orange, the blue, and the green. And we can continue in the next session. Thanks, everyone.